Hopefully you've had a chance to try out this problem. I'm now going to walk through detailed solutions. And this problem hopefully allows you to have kind of a quick and easy double check based on what we did previously when we calculated the amount of oxygen we would need to react with our 1.47 grams of glycine. And so going into this, I expect my glycine to be my limiting reactant here rather than my oxygen um, from that. So looking at our chemical reaction we developed previously with our glycine and oxygen reacting to form urea, carbon dioxide, and water, we were able to balance this and find that we would produce 3 carbon dioxide and 3 water molecules and 1 urea from a reaction with 3 oxygen and 2 glycine molecules. So we have our balanced reaction. For our conversion factors, we have 2 moles of our glycine will be equal to our 3 moles of oxygen, which will be equal to our 1 mole of urea, and will be equal to 3 moles of carbon dioxide and 3 moles of H2O. And in this problem, we really care about our carbon dioxide ratio to our oxygen and our glycine. I'm going to write down our molecular weights for these as well. Our molecular weight for glycine, C2H5NO2. Sorry, we're not looking to our amount of carbon dioxide, we're looking at urea. We did carbon dioxide in our previous example problem. Our goal here is urea. So let's continue writing out our molar masses. So we previously determined the molar mass of glycine was 75.065 grams per mole. The molar mass of oxygen we previously calculated as 31.998 grams per mole. And the molar mass of our urea is going to be 60.055 grams per mole. And these are just coming from our periodic table and adding up the total mass from each of the different elements with one another. So in a previous example lecture video, we walked through calculating the mass of urea that forms from 1.47 grams of our glycine. I'm just going to put it down here as a reminder and not spend as much time on it. And then we'll get to our calculation from our 2 grams of oxygen. So when we did this, we multiplied it by the inverse of the molar mass of our glycine. So that way we were able to have this in units of moles of glycine. And then we did our actual conversion into the units of our desired chemical, which is moles of urea, which is going to be a 1:2 ratio. So 1 mole of urea divided by our 2 moles of our glycine. And then we converted into the actual mass using that molar mass of urea, which is 60.055 grams per mole, and determined that we would produce 0.588 grams of urea. So now this is the value if of what we'll produce if our glycine is the limiting reactant. So now we need to compare, and we need to compare to oxygen. So we'll start with our 2.0 grams of oxygen and set up our stoichiometry problem, which will always be 3 steps if we're going to mass. To calculate the mass we'll have of urea from O2. So the first step is I'm going to put in my molar mass of oxygen and convert to moles of O2. using this 31.998 grams in every 1 mole of oxygen. Now that I'm in moles of oxygen for my units, I really need to get into the same units as our previous problem and figure out this mole of urea. So I'll produce 1 mole of urea for every 3 moles of my O2 that actually react. And then to get to the mass of urea, I just need to use that molar mass again, which is that 60.055 grams for every 1 mole of my urea, which is CH4N2O. So if I go ahead and plug this into my calculator, I'll get a value that is about 1.25 grams of urea. Now, this is what will form if oxygen is the limiting reactant. And that's because we started with the amount of oxygen that we had here. So now I compare. And whichever one is the smallest, which is this one right here, this 0.558, that is the amount I actually make. So the amount of urea I produce is this 0.5888, which means that my glycine is my limiting reactant. And that means I'll have an excess of oxygen, or I'll have some oxygen left over at the end of this reaction after all of that glycine has reacted.